This is a 1 Hz waveform, meaning each cycle lasts 1 second. So what kind of electronic component can generate such a waveform with minimal circuitry? The 555 timer can produce a 1 Hz signal, but it's not very accurate. Small variations in resistors or capacitors can affect the frequency. Using a microcontroller can give precise 1 Hz output through programming, but that feels like overkill for such a simple task. Now let's look at a method using a crystal oscillator. Here we use a 32.768 kHz crystal. With the right external circuit, it generates 768 cycles per second. Since 32,768 is 2, we can divide the frequency down step by step to get 1 Hz. How do we divide the frequency? A D-type flip-flop does the job well. Here's its internal logic. It's made of logic gates. But we don't need to go deep into that. This is its symbol. The clock input, data input D, and outputs Q and not Q. Here's how it works. If D is set to 1, Q stays low until the rising edge of the clock signal, then Q outputs 1 and not Q outputs 0. If we connect not Q back to the D input, the output toggles with every clock pulse. This halves the frequency, so if the input is 2 Hz, the output Q is 1 Hz. That's frequency division. Feeding the 32.768 kHz clock into the first flip-flop gives 16.38 for kHz at the output. By cascading 15 D flip-flops, we can divide it down to exactly 1 Hz. In practice, this can be done using integrated circuits. For example, the CD4060 and 74HC74 combo. CD4060 is a 14-stage binary counter. It's essentially 14 flip-flops with a built-in oscillator that works with a 32.768 kHz crystal. Its final output is 2 Hz. Since we need 15 divisions, we ray short by 1 flip-flop. This is where the 74HC74 comes in. It contains 2 flip-flops. We only need 1 to divide 2 Hz down to 1 Hz. Technically, you could use 2 CD4060 chips to get 1 Hz, but that wastes most of the second chip. Using a 74HC74 makes better use of resources.